All right, our next speaker this afternoon is Ryan Tsiao. Ryan's joined us from UCR and has been working this summer with Nima. Today, he'll tell us about their project together, spectroscopic confirmation and gas phase metallicity analysis of a protocluster at redshift 2.46.
Thank you for that amazing introduction, and thank you to everyone for being here. I had a lot of fun working on this project, and I'm excited to show you what I produced. So first, we need to discuss what a protocluster is. So a protocluster is a predecessor to a fully developed cluster of galaxies. They are high-density regions of dark matter and early galaxies, where the galaxies orbit each other in chaotic orbits rather than in stable ones. So classically, the identification of these protoclusters has been largely dependent on their properties, where these galaxies can emit at different wavelengths and therefore require different observation methods to detect them. However, the way that my protocluster detection method differs, or the one I use for this study, is it uses Lyman alpha tomography, which identifies the protocluster as a large-scale region of Lyman alpha absorption. And you can see here, that's demonstrated here on this absorption map, where the large-scale region of Lyman alpha absorptions are shown in red. Now, these are both protoclusters. The one in the bottom right is the one I'm studying in this study, and the one in the top left is a protocluster that we tried observing at the same time, but we didn't actually have enough nights to do so. But the reason why we're so interested in these protoclusters is because it can help us understand the early universe. And one way that it helps us understand that protoclusters help us understand the early universe is through galaxy evolution. So the density of the universe around a galaxy or the environment has been long suspected to tie into the key processes that drive galaxy evolution. However, there is no direct correlation between environment density and the key processes. So we have to use metallicity as a bit of a go-between. So, and the reason we use metallicity is because we know it ties into key processes like the star formation rate and the gas inflow and outflow. But the relation that's in question is the relation between the environment density and the metallicity. So this relation has been studied before and multiple other studies that have all returned discrepant results. Some claiming that there's no relation between the two at all, others claiming that an overdense environment results in a metal poor galaxy, or that they could even result in metal rich galaxies. And these discrepant results are all shown here, where each set of points connected by lines is a protocluster, and the ones above the zero mark are considered metal rich, while the ones below the zero mark are considered metal poor. And as you can see, this graph is pretty filled out. They're all over the place, which means that there's a problem that needs to be looked into. And that's what my study aims to do. I aim to input my own data into this discussion and see if I can make an impact. So, but in order to do that, I first had to obtain the data, and how my mentor went about observing the protocluster I would look at is he selected it from the Lyman alpha tomography IMAX survey, or LATTICE, a 3D map of intergalactic medium absorption. The density map, or the absorption map that I showed earlier, was a snapshot from LATTICE. And LATTICE is the survey that found my protocluster as a region of Lyman alpha absorption. I also, so then my mentor, once he knew where to look, he observed this region of sky with a Mossbauer instrument at Keck observatories using near IR K-band spectroscopy, and he collected the data over a span of 3 half-nights. And once we had this data, the most raw visualization we can make with it is a 2D spectrum, which is shown at the top right here. I had about 96 of these, and I found H alpha and then 2 lines in only 43 of them. So once I combed through all of these, and I was looking for these 2 features, because those are arguably the most important features that these spectra could give me. So once I had found these, I converted these 2D spectra to 1D spectra using a package called Pipet, and you can see the correlation between the H alpha and N2 lines here to the H alpha and N2 peaks in the 1D spectrum. And these visualizations of the spectra each serve different purposes. So the 2D spectra allow us to determine redshifts for the various galaxies within the protocluster. So the idea of this is so we obtain a bunch of redshifts, we can put them into a histogram, and there should be a peak at around 2.46 that confirms that this is a protocluster, and this is something that we should be looking at. On the other hand, for 1D spectra, we can obtain the metallicity from these 1D spectra by finding the H alpha and N2 line measurements, which directly correspond to the area under the H alpha and N2 curves. So once we have this ratio of the N2 area over the H alpha area, we could use that to find the metallicity. However, this is a very nice spectrum that I found. A lot of them didn't have very clear N2 lines. Almost all of them didn't. So in order to get an idea of the holistic metallicity for the entire protocluster, I had to stack a lot of these singular spectra on top of each other to try to bring up that N2 line a bit so we could measure it and detect it. Now, these are the two composites I was able to make using this process. There's a few things I did to the galaxies before I put them into their composites. So I'm going to talk a little bit about that. So the first thing I did is I took out active galactic nuclei and flat spectra. So the flat spectra were spectra that were just contributing noise and had no visible peak, but the active galactic nuclei, they don't fit within our gas phase oxygen abundance calibration in Pettini and Padgell's 2004 paper. They don't fit within it because this was calibrated for star-forming galaxies and not AGNs. So I had to take those out. Once I did, I cut down my 43 galaxies to 36, and I split those 36 galaxies into two stellar mass bins. And I split it right down the middle. So I found the median stellar mass, which is about 10 to the 9.5 stellar masses, and the ones below that end up in bin 1, and the ones above that end up in bin 2. And there was a few other things I did to make these composites, but for sake of time, I'm going to go over how I got my oxygen abundance values. Feel free to ask about more about the stacking process after my talk. But for the oxygen abundance values, the way I found them is I found the area under the H alpha peak, like I was saying before, and I found the area under the N2 peak, and I put those into a ratio and plugged it into the gas phase oxygen abundance calibration, which then spat out an oxygen abundance value, which does come with an uncomfortably sizable redshift here, and that is because the N2 peak right here isn't escaping the noise, which is something that I'm going to cover in my next steps slide and makes these results more preliminary than anything else. So this yielded some interesting results. The most interesting being I was able to confirm the protocluster. So we do see a peak here at 2.46, but I got a little bit more than I bargained for with this one, because there's also another peak at redshift 2.42. This is the redshift histogram I was talking about. All 43 galaxies are on here. And you see them gathering at the 2.46 line and the 2.42 line. So that implies that I actually detected two protoclusters in my observation. And we weren't expecting to find the one at redshift 2.42. It just happened to be in the line of sight, and we were able to get some galaxies from it. And this has some very cool impacts onto the mass metallicity relation, since it's not only covering one protocluster, but it's capturing the diversity of two. And this is my mass metallicity relation. So the idea of this graph is to compare the protocluster galaxies, which are in a overdense environment and should have been somewhat affected by that environment. And we're comparing it to field galaxies that at a similar redshift that are outside of that environment and should be not as impacted, and therefore we're using them as somewhat similar to a control group. So this is where the metallicity for my protocluster galaxy should be up here. But as you can see, it's a bit lower, and which would imply that my protocluster was actually metal deficient. So I was able to preliminarily answer the question of whether or not how the environment affects protocluster galaxies, and it makes them metal deficient. But there is still a lot of work to be done here. As you can see, like I talked about before, the error bars are still uncomfortably high. And one thing I do want to touch on before I move on from this slide is that the reason I used the field galaxies from Satari's 2021 paper is because they used the same calibration as me. So these results are very comparable. But my next steps all revolve around decreasing my error bars, because was my main issue for this entire project. And I want to decrease these error bars by increasing the sample size. And the way I aim to increase the sample size is by replacing the data that I reduced using Pipette with data that I reduced using Mossfire DRP. And the reason I feel like this will make a difference is because my mentor actually already reduced the data with Mossfire DRP, and he assigned me to reduce the data with Pipette as practice, but he actually ended up with more galaxies than I did with his Mossfire DRP reduction. So we're going to compare the two. If the Mossfire DRP galaxies are valid, and since there's more of them, they'll hopefully result in a much higher N2 peak in our composites and a better N2 detection, which will lead to lower error bars. And we're going to try to look at these protoclusters separately now that we know that there are two. For this, we don't really, decreasing the sample size will make the N2 harder to detect. And given all the issues I've had trying to get the N2 peak to be detected, I don't really think this will work out, but we're going to at least try. And then we're also going to exclude any galaxies that are not in the peak of the redshift histogram, meaning that the galaxies that are kind of at the edge of the protocluster or not in the protocluster at all are going to be excluded from the study. So that's essentially it for me. Thank you all for listening.
Great, nice work, Ryan. Do we have questions? Nice.
Great talk, thanks. So as you just commented, your error bars are larger than we'd like.
Yes.
So do you say that it's maybe a little too soon to say for sure that your sample is metal deficient compared to the other sample? It looks like
yes.
It's like 1 sigma, yeah, right?
Yes, it is a bit too soon to make any concrete conclusions from this, but for the scope of this internship, I'm saying that's metal deficient, but there's still a lot of work to be done there, and there's still a lot of I still have to process a whole new set of reduced data, so there's still a lot of work to be done, and this isn't my final answer.
Thanks.
Any other questions for Ryan? Anna.
But going in the other direction, where for the larger error bars, if you were to plot the one galaxy where you could see, or maybe one galaxy where you directly see oxygen and nitrogen and measure the mass, where would they be? What's the plot?
Yes, so I've seen plots like that. I wasn't able to do that because a lot of the one that I showed you that had a very clear N2 detection, that was 1 in like probably 4. A lot of them were a lot of them did not have any N2 at all, so I wasn't able to do that. But they're also, they would be anywhere kind of in, they would just kind of be surrounding the line. I don't really exactly know how else to describe that, but they would be from the graphs I've seen, people that did do that, I did want to do that, ask my mentor. He was like, yeah, in our dreams, right? Because our spectra were not that nice, but they look kind of like a bit of a cloud around this line.
Any other questions? All right, let's thank Ryan again.